Well, welcome everybody. It's so good to see all of your names and faces on the screen. I'll just introduce myself and then ask you to do the same a little bit through a chat box, and then we'll go ahead and get started. So of course, my name is Cindy Leary. I'm a statistician at the University of Montana in the School of Public and Community Health Sciences. I used to be a lecturer here at the university and taught introductory statistics for about 10 years. And so you'll see a lot of shadows of that type of material in this course that I put together for y'all. But hopefully it will kind of pull all together some of the really common themes that I think that are really pertinent and essential for us to be good consumers of data in public health. So again, welcome. So just so that I can get familiar with the chat box and get familiar with your names and who you are, and other people that are on video or on the call can also know who they're sharing class with. I'd love for you to, in the chat box, and you can skip any of these if you like, but enter those 7 items for me, just so I can kind of get some idea of who's on the class, and just get everyone kind of seeing who else is with them. So if you can take a minute to answer those questions, you can skip any that you don't want to answer, but just a fun little start to the class. Well, thanks to everyone. As anyone's, wanting, if you can feel free to keep adding in there. But it's so nice to just see some details about who's on the call. It looks like we have a lot of different people from different areas in public health and different experiences with different softwares and statistics. So should have fun with that. Let me tell you just a little bit about myself. So, of course, I'm Cindy Leary. I live in Missoula, and I currently heavily use R statistical language, which is what you'll see all the graphics have been made in. I'm familiar with Stata, PSS, ArcMap, and GIS, and I secretly love StatCrunch, which I'll say a little bit more about, which is this online statistical software that's just super easy for stat students to just kind of get their hands dirty with data without having to have a steep learning curve. So I like throwing data in there when I just need a quick and dirty analysis. And I'm currently working from home, except for today. I snuck into the math department today to be in my office, but I'm currently working from home. Love seeing those happy faces on the hiking trails. I'll just tell you a quick story with coming out of, hibernation with everyone. I love in the spring how everyone just seems to be so social. And I was out with my kids the other day, and this woman practically, ran us down to come, bring us back up the mountain to show us that she found these calypso orchids up Blue Mountain. So I just had to show a picture of this calypso orchid because it was so sweet that she just really wanted to share this with us. And I just love that community of springtime. And I'm currently doing a lot of research in public health. And I love teaching as well, although I'm not doing much teaching right now. My current research projects involve assessing health effects of air pollution, and that involves multiple different grants. So I'm grant funded on those different projects. So that's what I'm doing right now. Okay, without further ado, just a little bit of motivation. And so why should public health professionals maintain statistical literacy skills and operational skills in statistics? Well, being that you all are here, you probably find the value in it already without me having to say so. But it can provide us with a whole host of skills, this ability to identify specific health needs, be able to communicate with our peers, be able to read peer-reviewed articles, be able to effectively compare local conditions to those occurring on a national or world level, And, you know, just to be a leader in your field. I think that there are so many amazing skills that statistics can give to you in so many different ways. And so I don't think it's a bad field for anyone to study, no matter if you're in public health or, you know, an art major. It's just a wonderful field of study. Okay, so now I know that we're not in the field of education, but I just think that this is a really nice video to get us started about how important statistics is for our world to be better communicators. It's just a 2.5-minute video, and it's a little dated. It's during the Obama era, but which you'll notice right away. But we'll get it started here.
Hey, Cindy, are we supposed to be hearing sound right now?
Yeah, I don't hear anything either.
Okay, no sound, huh? Any ideas? Maybe.
Little volume button at the bottom there. The sliders all the way up next to the play icon. Okay.
Yeah.
Let me see real fast.
Emily, do you have all of us muted on your end? Except for Cindy, maybe it's, I don't know, I'm guessing.
You guys are muted. Cindy is not.
I wonder if somehow that's muting Arthur Benjamin too.
Yeah.
Let's see. I unmuted everybody. You can try.
Try it one more time.
Yeah.
Okay.
It's not working.
Nope. Dang it.
Working.
Yeah, I was thinking that too. Jenny mentioned in the chat, maybe going directly to YouTube.
Yeah, we could. I was going to say we could open up if you've got a second screen and just go there and.
Okay.
Yeah.
Since it's embedded in the slides, it might be.
Let's see here. So maybe stop sharing for this one.
Yeah, I was gonna say you can stop sharing right now if you want. Find it on YouTube and then share again.
Okay. Well, and if this doesn't, I don't want to waste too much time. I can paraphrase.
To get sound, you might have to change your Zoom audio input from headset to PC output. Yeah, that part is a little new to me. Always learning.
That's okay. Let's see here. So I'm going to do.
Yeah, I just pulled it up on my other screen. I'm listening to it.
Can you hear the ad? Does that work at all? No. Okay. That's okay. I can send that. Actually, I can just send it to you all in an email, and maybe we can figure it out by the time the next video comes up. But basically, what Arthur Benjamin is saying, and let me go back to my other screen now. So stop share. Share.
And certainly if you have the link, you can put that in the chat box as well, and folks can access it.
Okay, good idea. I like it.
Nice.
Dave threw it in there.
I like your idea, Sarah. Homework, everybody.
Oh, perfect. Get rid of it.
Okay.
Do you want me to try and play it and share it real fast?
That's okay. You know, maybe which one I would really love you to do that for is the Hans Rosling one at the end of end of the graphics section.
Okay.
That's like that's the one that I really love.
Okay, I will go find it and figure it out.
Okay, let's see here. So I just want to make sure that I'm a little bit unclear about what you can see. Do you see my my PowerPoint screen right now?
Yeah, we see the James Lind.
Thank you. Okay.
Yes.
So we have Arthur Benjamin, and he was just basically just talking about how a lot of our high school students, whether they're going to go into science or whether they're going to go into social sciences or art, that a lot of them have this like plateau of calculus that they're going for. And he's making the case that, you know, for most students, it would make a lot more sense for the plateau class to be statistics because it's so important for all life skills and such a really important class to just be a consumer of data and statistics. So next, so then now I just have as a background, I'm outlining just some historical people who have been kind of pioneers in the field of statistics, and I just wanted to share a little bit about them. And we'll revisit a couple of these situations later on when we look at these other topics. But I just want to kind of share a little bit about each of them and what they did for the field of statistics. So the first one is James Lind, and back in the 1700s, he was a surgeon on a ship, and he was trying to solve this problem of scurvy. And in the process, his work is the first ever documented clinical trial, you know, a randomized clinical trial where, you know, we're trying to find a treatment for a disease. And so it was through this randomized trial where he split 12 different people on the ship who had scurvy, and randomly decided who was going to get a quart of cider per day. The other two were getting 25 drops of this elixir, and then 2 of them got some vinegar, 2 of them got seawater, 2 of them got nutmeg, purgative electuary 3 times a day, and then the last got these oranges and 1 lemon, which of course then was this vitamin C treatment that ended up being the cure for scurvy. And so that's the first ever documented clinical trial. Then we have Florence Nightingale, and she was in the 1800s. Her father educated her at home in mathematics, and kind of, you know, statistics really wasn't a field, but she became a nurse, and she was just a pioneer in public health overall. But she's also known for being a statistician, collecting data and really solving one of the prominent problems in the Crimean War, where she was seeing just lots and lots of deaths, and realizing and showing everyone with her skills that those deaths were actually avoidable because they were really not due to actual war inflicted wounds. It was actually due to disease that was preventable from just basic cleanliness. So she developed this coxcomb graph, which is admittedly a little bit hard to read, but you have to just really appreciate the beauty and with the accuracy that she constructed this by hand, and the forethought to try and put this time plot together. So you can see that, this on the right side is April 1854 to 1855, and then it goes on 1855 to 1856. And you can look at this, maybe look at these plots or these slides later and just really take a look at what's going on here. But each of these little pie wedges represents a month, and the light blue represents deaths that are basically avoidable. And so she was showing how they had just been growing and growing disproportionately to the other deaths. And then after she was able to implement some of those or help the Army implement some of these techniques, then those deaths were started to be avoided. The next one is this Semmelweis, and I highly recommend, if you have the time, to look on this Radiolab article. It is just, I mean, all of their work is wonderful, but this is a fascinating story about a physician who noticed that there were all of these mothers who were giving birth and in this maternity ward. And he noticed that all of the mothers who were getting delivered by doctors, they had a much higher rate of death than those that were getting delivered from midwives. And so he recognized that these doctors were actually doing autopsies in the morning and then coming to deliver babies in the afternoon. And they had no idea about hand washing, which now we're vigorously doing like 10 times a day. And they actually fought him on it, like this wonderful preventative measure. And he was, you know, they actually just kind of shut him out because of these ideas that he was bringing, because he couldn't come up with a mechanism for why these deaths were happening. He just called them cadaver cells because he didn't have a name for bacteria yet. So, and so also to show that not just these statistical methods or methods for observational studies or experiments, but also just the ability to come forth and do what's right, and bring forth information that sometimes people don't actually want to hear. Then we have Jonas Salk, and you all have probably studied some of the information that comes from this fascinating story of vaccination research and public support for this giant experimental trial. And we'll talk a little bit more about this, but when we go back and start talking about experimental design. So I won't say much more about that at the interest of time. But there was also a fabulous person from DPHHS that came and gave a seminar at UMontana, I think last year, about this, the vaccine trial, and specifically for Montana. And that was really fascinating as well. And then I had to throw in, of course, now we're in this new public health crisis where we have lots of different studies going on, lots of people out there trying to find, you know, cures, vaccines, any types of therapies. So there's, you know, a lot of talk about this convalescent plasma therapy that can take plasma from someone who has already been infected with COVID-19 and give that plasma to someone who's suffering from COVID-19, and you know, trying to study, is this really an effective treatment, and how do we go about actually doing that? So those are the historical and very present just kind of examples that I want to give of statisticians and pioneers in public health. And then lastly, I just want to, oh, do you guys hear that feedback? It's just me.
No, it's all good.
Okay. And so lastly, just showing this very recent paper that is actually not even published yet, but these results have been presented, and the paper, it's just been submitted for publication. And so basically it's that these epidemiologists from Harvard Medical School are finding this association with air pollution and a higher death rate from COVID-19. And so we're going to look at that as well and kind of analyze a little bit more about what's going on with this study. So those are just some examples that I wanted to bring up with current public health research that's happening. Okay. So let me just tell you kind of where we're going. So basically, I know that we all have different familiarities with data and graphics and data cleaning and analysis. But I hope that even for those of you who are, very well versed in statistics and analysis, hopefully you'll still find some little nuggets in there. And at the very least, you'll have fun seeing the data that I've put together for you. So just talking about data in the first section and really focusing on a lot of different, very basic graphs. But in my opinion, the most important part about exploratory analysis. Then we're going to learn about different sampling designs and just some of the terminology and things that we want to look out for when conducting samples, and then also just reading literature where samples have been conducted. And then really starting to explore this idea of sampling distributions so that we can better understand what hypothesis test results mean and confidence intervals mean. And then looking at observational studies and experiments, moving on to inference procedures, and then we'll wrap up. Lots of hopefully interesting and exciting examples throughout the rest of the talk here. Great. So let's see here. I think, so we're at, let's see here. Oh, I am going to do something real quick. Actually, if you guys want to, I'm trying to think of when, on our agenda, I have that we were going to take a 5-minute break, but I'm also a little bit ahead of schedule. So I'm going to take a second and send this really exciting video so that we can listen to it in the next section here. So if you can just take a break, drink some good coffee, and I'll be right back. Okay, everybody ready? Okay, so the next section is about just organizing data, learning about what your variables are, defining your variables, organizing them, and then we'll start to look at some different graphical and summary techniques. I guess this section is really, first of all, about the importance of data cleaning and organizing. And I feel like my jump from really teaching to research, I guess I never realized how much was involved when, you get a data set or, you're collecting data. I mean, I would say easily 60% to 70% of my time is spent on the data cleaning and organizing and just documenting everything and making sure that, everything is as it should be, so that we're, so that it's all, just clearly organized and that we understand what's actually being represented in our data. And then I also just want to talk for a minute about statistical software. So for some of you, it seems like, you're using SAS, SPSS, but then I saw a few of you who aren't yet using any software, which is totally fine as well. And then I neglected Minitab. I saw somebody else on there who said Minitab. But, if you're questioning what statistical software to use, I mean, these are just some of the questions that I'd be asking. Generally, a huge part of it is what anyone you're working with is going to be using. So what your coworkers are using, what's going to allow you to best communicate your ideas to your audience or complete your work tasks. So if you need to be able to, run simulations or do different things, then that's really going to drive what, what statistical software you really use. And what is available to you, given that there's these licenses that are quite cost prohibitive. So I've just made a little bit of a list I, of course, am biased with R because that's what I've kind of been raised on. And I just think it's an excellent software that's free, and it has so much documentation out there. But it does have a fairly steep learning curve to begin with because it's a scripting language. But there are some new kind of GUIs out there that can help you get a more menu-based approach there as well. So I would highly recommend R if you're looking for a software. SPSS is a great menu-based option. SAS I don't know a lot about, but I know it's widely used in health-related fields and has excellent capabilities, but it's quite expensive. Stata I feel like is a really nice happy medium between, say, something like R and SAS, where it has a lot of nice menu options. It's more reasonably priced. StatCrunch is that guilty pleasure that I told you about, but it's only $25 a year, and it's very similar to some of the SPSS kind of, just like tabular kind of menu-based options, but it can do a lot of pretty sophisticated analysis. So, I mean, if you're just looking for a quick and dirty software, it's completely online, so it's a cloud-based software. So if you have sensitive data, that's not great. And then Jump, which seems like it would be so much fun, but it's really expensive, so I haven't jumped into that one. But it seems like it would be just a really user-friendly and really dynamic software. And then, of course, ArcGIS, ArcMap tools for visualizing and analyzing spatial data. So those are some different statistical softwares. If I don't know a lot about multiple softwares, but certainly if you have any questions about R or SPSS or StatCrunch, I'm more than happy to help you out, getting you up to speed or started on one of those. Okay, so for data, was there a question? No. So for data cleaning and organizing, this is often one of the most important and time-consuming pieces of your project. So, if someone hands you a data set that you haven't been a part of collecting, you have to learn all about, all the W's, right? Where, who do these actually represent? What is being collected? When were they collected? Why? You might have to read about the different survey questions that were actually asked in order to get the answers. A lot of times those answers are in a not very friendly format. Maybe there's a lot of typos to where you have to go in and correct them. And that can be a really important challenge, this piece of cleaning your data. That point of cleaning your data is something that I think can be done very incorrectly. In my opinion, if you have the ability to do it with, say, R or SAS, some type of scripting language, I have an opinion that I think that should all be done through code, so that you're not going in and editing a spreadsheet by hand so no one actually knows what's been changed. So you want everything to be reproducible, right? So you can actually come to your team or to another researcher and show them precisely what has been changed in those data. Because once you make those changes, and if you don't have any systematic way of making those changes, then I feel like you're going to be prone to error, and no one really knows what was actually done to those data in order to clean them. So if at all possible, you can do a lot of that through code so that everyone knows what's been done to the data and nothing actually ever gets deleted. Taking the time to communicate with co-researchers, your superiors, people who've given you the data, making sure to communicate with them, taking the time to sort through those project goals so that what you're actually producing for those data are, you know, are what's needed. So, you know, and then also asking, you know, I always ask myself, what is future Cindy going to need to see in 2 weeks when she cannot remember what she did, right? And so making sure to document what you've done, right? Create a data dictionary. And this seems like the simplest thing in the world, that everyone would have thought of this, but, you know, when I started doing research, this was like, I mean, I don't know, for some reason, this was just like an aha for me, because it saved me so much time once I started doing this. I mean, it's so simple. Just for every single variable, make a row, you know, document what each one, you know, what units are, any description, like where did they come from? What was the survey question that produced that variable? You know, all these different things. And then even another column of notes, like maybe you're deciding to, you know, edit or clean that variable in some way. And so you can add that into the dictionary. So then when someone comes and wants to look at that data 6 months from now, all you have to do is say, yep, here's the data dictionary, here's what everything means. And, or if you come to it 6 months later, you can remember everything, which is usually the case for me. So I just highly recommend just taking those extra 10 minutes just to make sure that you document everything, make everything reproducible, and it makes you a better researcher, makes you a better team member, and I think it's just really important to produce good research, good communication.
Cindy, you have 2 questions in the box. Nathan asks, this can be done in R.
Let's see here.
And then Lisa has a question.
So yeah, Nathan, you know, I don't have an example right now, but I mean, for example, I'll just kind of try to explain kind of what I would do. So let's say that I have a bunch of heights, for example, and maybe, I shouldn't say maybe, this actually happened to me a couple of weeks ago, where half of the heights were written in inches, half of them were written in centimeters, and then another, like, well, another half were written in, you know, some other thing that I had to try and decipher. And so, you know, so I would in R create this variable that was, say, like new height. And I would say, okay, new height is equal to the old height, and then try and come up with a way to decide if that was in centimeters or inches, and convert that within the code from centimeters to inches or inches to centimeters. And then come up with other things, like if there's a lot of misspellings of a variable, I would just say, okay, you know, everything that's spelled this way, turn it to the right spelling. So it's a way, using brackets on a variable, that you can, you know, just it's slightly time consuming, but I do think it's worth it to be able to make that a documentable process when you're cleaning. Does that make sense? Let's see, can you give a concrete example of how you code a variable and responses? Let's see here. Code as in, yeah, I'm trying to think of if I can. So the question is just if I could give a concrete example of how I would give a code a variable in responses.
Cindy, on
Yeah.
the spreadsheet that you sent out, a good example would be the county, right? You could code those counties on a column.
Yeah, I guess I was just debating on whether that was a precise question for R or, yeah, Lisa, is that specifically for R, or is that just in general?
Yeah, thanks. I think sometimes we throw out coding and I'm always like, what do we mean exactly by coding? And so I have R, and so an R example would be awesome.
Oh, okay, great. So, well, one way, I wonder if, I'm just trying to decide if I should just go into R and show how I would do that. Maybe we should go to the data table first. So I mean, it's really just if you think of like a vector variable of, say, counties, and you want to have a vector that has those county names, in R, you would just be able to get that. I think maybe I should just go ahead and open
Cindy,
up.
I think maybe her question is for people that have just used a menu-driven stat package, they don't understand coding. So
Right.
writing code versus the menu. So I think that's the base of the question.
Yeah, thank you. I appreciate that. Yeah, so for those menu-based, I think that you can definitely still, if you're not able to change it within, like the R code, I think there's, you can still maybe just create a document, even just like a Word document explaining everything you changed in the data. And then keeping an old version of the data and then have a new version of the data. That way, you have a list of everything that's been changed, and then you can still go back to the old data in order to be able to compare them. The only problem is just with really large data sets, to actually just eye those changes is a little difficult. But even just that documentation is the most important part, in my opinion.
Thanks. That's helpful, Cindy. And so just one clarifying question for coding, it's like ones and zeros, right? So we can then quantify those amounts. Is that kind of the gist of it?
Yeah, I mean, for the coding, it's like, let's say you have a variable that has A, B, and C, and then you say, well, I want to change all the C's to D's instead. So it's just a way in the code to be able to just, instead of having to go through in Excel and sort them and then change them all, you can just say, okay, anything that's a C, let's change it to a D. And you can do that within the code. And hopefully when we get to looking at some spreadsheets, it'll be a little bit better as well to look through. Great. And this one, I wasn't quite sure where this one would go, but I just kind of stuck it in here because I wanted to make sure that I had time to talk about it. This is, again, something that I think, we don't talk a lot about in statistics, but it's one of the most important parts of my job, is being able to communicate and make myself into a leader on projects. And these are the ways that I have learned to be able to do that and feel like I'm doing a good job and push projects forward. So I feel like I talk a lot, but being a good listener, really listening to what, the goals of projects are, what people really want out of their data, creating timelines, goals, and standards. So that's really helpful for myself so that I can keep a schedule for myself and then communicate those with my peers, my coworkers, and my leaders as well. Consistently and clearly document your work and produce these timely updates. So this again goes along with kind of what we were just talking about, but really documenting what's been done. You can even create just like PowerPoint slides as journals just to explain to yourself what you did that day, produce timely updates. And I think it really helps you keep on task if you're trying to produce those timely updates to your team as well. And then also just always kind of keeping on task, making sure to ask those clarifying questions to make sure that you're all working toward those same objectives. In my experience, everybody has different fields that they're working in, but, it's for me to just talk about what I'm doing as opposed to preparing documents and being able to actually show everyone. That is really helpful for me. So, you know, just for a meeting, always just having a document ready with, you know, what I've done, making them very readable, approachable, so they're not too confusing, so people can follow along and not feel like they can't keep up. And then, of course, just being willing to learn new methods, you know, volunteer for something that maybe makes you uncomfortable, study in a new field. I just think that that can lead to gems that you learn new things and meet new challenges and new people. And then just make the extra effort to produce results or complete tasks that might be novel or add unexpected value to the project. These often can be the most fun, and they can end up leading to really interesting discoveries. And so just a few little nuggets that I felt like were important to me in my work. So I just wanted to share them. Okay, so some of my slides are a little bit terminology heavy, so I apologize, but statistics is full of language, and there are things that are very important that we speak in the same language. So I just want to make sure that we're all clear when I talk about these different, specifically the term statistics and variable, that we're all on the same page with what those mean. And I'll show you a concrete example, well, multiple concrete examples of variables and statistics here in just a few minutes. So data are any, and so notice that I said are, so data is actually plural. So just kind of throwing that out there. So data are any collection of numbers, characters, images, or other items which describe items of interest. Okay, and then statistics as a field. So there's two different statistics here. Statistics as a field is a way, there's a few different definitions, of course, but it's this way that we reason along with a collection of tools and methods that are designed to help us better understand the world. So that's the statistics as a field. And then within statistics, it's all about variables, and these are quantities or characteristics that are recorded on each object, case, or person that we're studying. And when we start looking at this awesome example that we've pulled together, then we are going to see that there are basically three types of variables. There's a few that kind of get thrown in the mix in there as well. And they're categorical, which are also called qualitative or discrete. There's quantitative, which are also called measurement variables. And then there are identifier variables. And our identifiers are exactly as they sound. They're just meant to identify a case uniquely. So they don't actually have statistical value to us, but they're extremely valuable to be able to match up data sets or know what the unique, like if we have, say, a time series set of data and there are multiple rows observed on the same person, then the identifier variable is going to be really important to us. So, so we definitely love those identifiers. They can make our lives easy, and they can make us cry when they somehow get deleted. So, so save those identifiers. And then when we have a categorical variable, you've probably heard of binary variables. Those are categorical variables that only have two categories. And whenever you're trying to figure out if you're dealing with a variable or a statistic, just remember that a variable varies from case to case. So it's a value, whether it's categorical or quantitative, that varies from case to case. Then statistics, plural, the last bullet, are those numerical calculations and summaries that are made on one or more variables. So for example, a sample mean height, a sample proportion of females in a group of individuals, sample standard deviation, sample proportion. These are all examples of statistics. So those are those main terms that I just want you to try and hang on to as we take a step back and introduce a data set, and then we're going to go through and do some analysis there. Okay, great. Okay, so there is this this website that belongs to a team of data scientists, and they attempt to quantify social distancing based on, I don't claim to fully understand all of the ways that they are getting these grades, but I just think it's really interesting. And I started looking at this data set a few weeks ago and have just been keeping an eye on it from time to time. This one was downloaded on May 4th, and we were kind of on a downhill slope for distancing, which makes sense with lots of things opening back up. So they basically are rating different counties on how well they adhere to social distancing based on just different things that they've calculated based on mobile data. So trying to figure out how far people are traveling compared to the average, how they're trying to estimate, you know, how close people are coming to one another compared to what is average. So I have to admit that while I did do a little bit of reading in some of their methodology, I just want to throw it out there that I don't put a huge amount of stock in these grades, and that this data set that we're going to look at is purely for educational purposes. So I don't want to, not that there's not any sensitive nature to it, but I don't want you to, you know, worry about our different counties. It's not that different, but I just wanting to put that disclaimer out there that this is a really novel thing that people are trying to do to try and measure social distancing. And I just thought it was really interesting and a really ripe thing to look at for our little class here. So, so the next one is just for Montana, and they break it down by county. And so I took this screenshot on May 4th, but I actually downloaded these distancing data on April 30th, I believe. And so I just went through and collected the distancing variables for each county in Montana. So we have a grade for each county. And then I also collected a few other variables as well. So you all might recognize this division of Montana, but I grabbed this from the Office of Public Instruction, but I've seen this division done in different Montana or state Montana organizations. I've seen this division in multiple scenarios. So basically, we have a social distancing grade for every county. And then we're going to have also what region that county came from. Okay, so for example, I'm here in Missoula, so we're going to be in region 5. Okay, and based on this orange, it looks like maybe we had a grade of F or D, but it's not. It's because I downloaded it earlier. We had a little bit higher grade for that social distancing. But so just want to give you an idea of what we're looking at here. So we have one categorical variable, which is going to be our social distancing variable. And then we have one categorical variable, which is going to be our region that we're coming from in the state, okay? So the first step that we were just talking about, we're gonna organize and tidy our data. So tidy data comes from a gentleman named Hadley Wickham, and he's an R guru. He's built a lot of different packages, and he has a tidy data package And I got to see him talk at a conference last year, and he's a really big proponent of having very tidy data, you know, kind of what we just talked about with documenting your all of your data cleaning, and then making sure that when you're organizing your data, that every row is a case and every column is a variable. So there's sometimes ways that you can kind of arrange them differently, but I'll strongly encourage you to adhere to that. So every row is a case, every column is going to be a variable. So this is now where I believe that Emily is going to try and get you all into a little breakout session. And I'm just going to have you all just answer a few questions about these data. And let's see, I don't know if I should, so maybe take a mental picture of that, not that you have to memorize the data, but just the basic organization of what those data look like. Note that each county has its own row, and then you have these 5 different columns for the different variables there. So, yeah, so if we can just do a little breakout, I don't know how long it'll take, like maybe 10 minutes, but you know, get to know your group members and then try and answer these 5 questions amongst your group. And then we'll come back and I'll have a couple of representatives from groups talk about it. Well, so Emily, I don't know how, if you have any like thoughts on how this has worked the best, but I was just thinking of maybe asking for, you know, 2 volunteers to maybe just give some, like, or first volunteer, maybe 1 volunteer for each item.
Sure.
So, and maybe perfectly, we had 5 different groups. So maybe 1 from each group for each question. How does that sound?
Sounds good.
So, so can someone from group 1, if you know if that you were group 1, if not, you know, just someone from one group, could volunteer to just talk about item 1. What are the data in that COVID spreadsheet, and what are the cases? In other words, what do those rows represent?
Make sure you guys unmute yourselves.
Yeah, this is Dave. Can you hear me?
Yep.
Yeah, thank you.
Okay. Well, I'll just jump in there then. So it looks as though it's data that was taken. It was organized by county. It includes the Montana County, the identifier variable is in the first column. Then we've got categorical variables for our county and our state, a region. And then we've got cases, which is actually quantitative. We've got a rate per 100,000. And then we've got a grade, well, again, categorical for distancing, whatever the A, B, C, D represents. And then we've got a quantitative variable for population.
Great, thanks so much, David. And I do want to just, I didn't realize this when I wrote this question. I do want to point out that, you know, I say what are the cases in item 1, and when I say that, that's really like what's being observed, and then but it's really confusing because we're looking at COVID cases. But so the data themselves, right, are all of these variables and rows combined, and the cases are the actual the counties really are the cases. By county is the row, and then of course, just like David, you said, then the quantitative variable is the number of cases, just like you said. But I just wanted to clarify that. Great, thank you. What about item number 3? Any group want to volunteer to talk about any statistics or relationships that they'd be interested in looking at?
This is Janet. One of the things that we talked about the relationships that we wanted to look at was, excuse me, we talked about how come some counties with 0 cases got a B and some counties with 0 cases got a C or a D, and what are the variables or the statistics that they've been using to determine that. How did they come up with that information?
Mm-hmm. Great, thank you, Janet. Yeah. Let's see here, and so, and also, in terms of looking at the data that are there, I agree that would be really interesting to figure out what precisely it is about these distancing variables that are, I assume that it's just that really low population density that they can't get those mobile data on enough people to be able to grade them. But then, in looking at relationships, thinking about, we'll look at this in just a minute with these graphics, but maybe, is there a relationship between, for those counties that do have a grade, are there different social distancing grades depending on what region of the state? So is there a different distribution of grade depending on what region you're in? That might be an interesting relationship to look at as well. How about item number 4? Does anybody have any graphic displays that they're thinking about looking at with these data?
I'll jump in there. We thought the grade as the x-axis and then the cases per 100,000 on the y.
Great.
Might be an interesting graph.
As kind of, and just doing kind of like a point plot there, kind of like a scatter plot almost.
Scatter plot, or maybe even like a bar graph with the
Mm-hmm.
means and standard deviation.
Mm-hmm.
We also
Great. Well, thank you.
discussed, this is Nina. We also discussed the use of the maps that are currently being used, and having the color coordination so that you can easily see very quickly where there's a lot of cases and things like that.
Nice.
That's
Yeah.
actually very helpful to get that visual.
Great, thank you. And lastly, item number 5, additional variables that you wish you had for these data to try and better study COVID-19 and social distancing.
This is Dave again. I just think there's a very potentially long list of things that could help tease out relationships. We could start with some basic things of gender and age and socioeconomic status, health status, and so on.
Yeah. Great. Thank you.
This is. Oh, go ahead. This is Will, and our group mostly talked about things we could do further with the data. So we talked about looking at, it would be interesting to look at the professions of these cases and kind of the nature of some of these cases as well, like if it's hospital related or daycare or nursing home, or if it's more of a community type thing. But then also drawing in some population density. So we probably need some area of the counties, since we already have population, looking at the road miles traveled and the distance, that typical distance that people have to travel in areas for things like to get groceries, to go to work if they're an essential worker. Because I know that with those gradings, the distance traveled was a major part of it. And so it's not as kind to rural areas.
Yeah.
And yeah, and then the urban-rural classification would also help with that.
Oh yeah, that would be a great one.
This is Emma, and kind of in that same vein of wanting to know the conditions surrounding each of the cases, like were they at work, just adding or maybe eliminating those whose exposure we know was at home, because social distancing wouldn't have affected household contacts. It would be interesting to know what numbers we were left with if we were really just looking at community acquired or work related and not household contact or travel cases.
This is Janet again, and Jancy doesn't have a microphone, but had commented in our group that knowing or having an overlay and looking at which counties have social transmission versus those, track that like the cases up in Toole County where they knew that they all came from the nursing home, looking at where they, if they were able to determine transmission source.
Yeah, right. Good point. Yeah, so it seems like, thank you everybody for all of your feedback. It seems like a lot of you are recognizing that while it's valuable to have these data at the county level, it would be really nice to have another data set that was where each row actually represented an actual person, where then you could get a more fine understanding of some of those features that you all are discussing, which I think is an excellent idea. But I also want to bring it back to show you that then that would change how these data would be organized. So you'd have, each row would then be a person. You would still have the county name, but then, you would have a bunch of Madison counties, well, not a bunch, 8. And then, and then a few Missoula counties and so on, repeated row by row for those different people that were in the same county. But so that would be just a completely different data set with the rows representing people instead of counties. But thank you for all of your feedback. So let's see, so we are at 9:40. And so I propose that if you all agree, if it's okay with everybody, that we go for another 10 minutes and look at some graphics with this, and then we'll take a short break. If that's amenable to everybody, we'll go ahead and look at some, hopefully some informative graphics, and I think some of which I heard a lot of you describing, but I just want to illustrate some of those from these data and move on here. So this is just a title page creating these and interpreting effective and informative graphics. So I say that precisely, effective and informative, and I'll allude to this a little bit later as well. But I just encourage you to, every time you're creating a graphic, just be really clear about what you're trying to represent. Try not to add too many bells and whistles that aren't actually adding information to your graph, or too many colors, too many fancy graphics. Just trying to go for what is going to educate my reader about what I'm trying to say about my data, and trying to go with that that framework, I think it's just served me well, just trying to keep things as simple as possible, which you wouldn't guess with all these plots that I have here. But this is just to kind of illustrate the host of options that we have for looking at both single variables, both categorical and quantitative, looking at relationships, and so on, which we'll discuss throughout the next few slides. So the next chart, or the next slide, is pretty text heavy, but I basically just wanted to separate the different variable types And to outline for you some of the basic, this is certainly not an exhaustive list, but these are some of the most common and basic graphics that are used for the different variable types. And every once in a while, you'll have, say, a variable that might be kind of in the middle. It might have some ordering to it, where you could use a couple of categorical methods, but then those orderings actually make make quantitative sense as well, to where you could use some quantitative methods as well. But this is just a basic framework for, okay, if I have categorical data, these are my basic options. I can make a pie chart, I can make a bar chart, I can look at frequencies or relative frequencies. So relative frequency just means, that the count divided by the total in the sample, and bar charts and segmented or side-by-side bar charts. And then, there are a few others that we could throw in there as well. And then there's this whole group of plots, and there are plenty more here as well for quantitative data. So here are two categorical data categorical variables that we have in our data set: the state region and the distancing grade. And then we have three quantitative variables. We have cases per 100,000, and population size, and again by county. So these are all of the quantitative plots that we have. And then we also have these different types of maps, which I know at least one person who does a lot of those based on one of the breakout groups. Will said that he does a lot of mapping, so he can educate us on those. I love maps, but I'm still working on my ARC skills, but R does have some mapping skills as well. And then we have time series data, which we don't have in our data set, but these are data that are organized by time. And some of you said, if we had more of like cases by time, that might be an interesting, graphic to analyze as well. And we could certainly track that down. But let's just go ahead and jump into some of our data and just start looking at some basic plots. So visualizing these categorical variables, I'm just putting this map up here just so you remember what each region associates with which counties, so that you can understand what they associate here with the bar graphs. So this pie chart and the bar graph are representing the exact same variable. They both are containing those percentages. Only the bar chart shows you an indication of what the counts are. You could certainly add a count label in this pie chart. Note that the bars are not touching. So that's to indicate that this is a categorical variable. Even though we have numbers here, those numbers are not quantifying anything. So we want to make sure that it's clear it's a categorical variable, because a histogram, which we'll talk about in the quantitative section, those bars are touching. So you want to make sure that the histogram has bars touching, the bar chart has that separation between the bars. And you want to make sure that these bars are exactly the same width, so that the only difference that you're seeing is the height of those bars, or in this case, the side length of these bars. That's the only difference, so that your eye can easily just look right at it and say, yeah, easily region 1 has the highest proportion of counties. So that's not necessarily population, but just the highest proportion of counties out of all those 56 counties. It has the highest proportion at 30%. And region 5 has the lowest proportion of counties with 12.5%. So I'm going to give you a quiz on the next slide, and if we're ready for that. Let's see if we're all good for that. Okay. So each one of these graphs below represents the same data. So exactly the same variables. There's nothing changed. So tell me which one you think is misleading. You can have more than one answer if you like, but choose which one you think is misleading.
Got lots of answers coming in. Got 13 of you so far, 14.
It's like a Who Wants to Be a Millionaire.
Yes, look at a game show. If only I had $1 million to give out. Let's see, we got 19, 20, almost got all of you. I know a few folks have to wander off for work duties, so it looks like we've got 20 of 27. So I think that'll work.
Okay, very good.
Let me end it, and I should be able to share it. There you go.
Okay.
Which is its own form of data graphic.
It is. It is. It's fascinating to me as well. And it's actually quite, so can everyone see the results? Can participants see the results?
Yes, they should be able to see them.
Okay, great. Okay, so we can all see that it seems like people think D is actually the most misleading in general. So, which is really interesting to me, actually. So in my opinion, so this is all opinion based, except for one of them, I would say that there's one that I think is misleading for sure. But so A, of course, you know, we have the ability to really really be able to pinpoint the differences between those regions in terms of the percentages. And those percentages are still accurate, but your eye just doesn't pick up on the differences as much because you have all of this empty space. So I would say that A isn't necessarily misleading, but it's not ideal either. So I would say, you know, to make your graphic more clear, that you should be able to scale that up to where the maximum is maybe at 25, so that you can, you know, that the bars are taking up most of the plot. B, it seems like most of you thought that one was pretty good. I agree. I think it's a good one. You know, you have those bars ordered 1 through 5, and then you have the percentages. And you know, the scaling seems good, so I feel like that one's pretty decent. So C is the one that worries me, because if you notice on the y-axis that right here where it gets cut off, that it doesn't actually start at 0. It's almost like it starts at like 6. So when it doesn't start at 0, it gives you this feeling that if you look at region 5, look at how much smaller region 5 looks compared to region 1. So it's almost a way of, not that someone would necessarily do this on purpose, but it would be an easy way of manipulating a graphic to making something seem different than it really is. So I would say if you really wanted to, you know, notice 5 versus 1, look back at B, and you'll see that does appear to be misleading when you have that smaller bar for that region 5. So I would say that C, in my opinion, is the most misleading. Now D is really interesting because one of the scripts that I have always orders the bars in terms of increasing frequency, just to make your eye easier to see. But I agree that it feels misleading because then the categories are not ordered. So then it gets confusing on how to read that. So I could go either way with whether that is a good idea to order those percentages. Sometimes it's really nice when you have a lot of categories to order them so that your eye can just really see where those differences are very clearly. So that's just my opinion, but a lot of this is what you think is going to most clearly communicate your data. I will go back and say that the pie chart, a lot of people like pie charts, but I'll just point out that if you're just looking at the shading and you're looking at, say, the difference between 19.6 and 16.1, that if you're just looking at the area, your eye doesn't really pick up that difference, or at least my eye doesn't. Whereas if you look at the bar chart, the difference between 19.6 and 16.1 is very clear to me. So I think that pie charts add a lot of, especially when there's maybe 2 or 3 categories, they can be a really nice additional flavor so that you can have multiple types of displays. But in my opinion, once you get more than 3 categories, it can be really hard to discern those areas. So just food for thought as you're thinking about your graphics and which ones are going to be the most clear to understand. Okay. So then we have another set of bar charts. So we have the region, and then we have the population size in thousands by region. So I thought this was really interesting. If you look at these state regions, so state region 1 has 30% of the counties, but state 1 has 7.8% of the actual population. So it's just kind of an interesting, you know, they're ordered in opposite directions. But, you know, state region 2 has 13.8% of the population, 16% of the counties. So just another bar chart. Now, let's say that we want to look at the relationship between categorical variables, social distancing, and state region. In other words, do different regions have different distributions of social distancing? So what we can do is create a table. This is called a two-way table, which we've all seen before. Okay, but we're, you know, for example, if I look at this two-way table, I see that there is one county that is from region 4 that had a social distancing of grade of A. Okay, and there were 8 counties that had that from region 4 that had a social distancing grade of B, and so on. So this is just what we call a two-way table. And we want to take this two-way table and make a graphic out of it, because my eyes don't really pick up on what, you know, where those differences really are by region. By just looking at those counts, I'd like to be able to get an overall distribution for each one. And so that's where we can make what's called a segmented bar graph. And these are 2 examples of segmented bar graphs. I'm going to first talk about the one on the bottom. So the one on the bottom is by count. So let's look at region 1 and look at these colorings here. So region 1 had 1 county that had a grade of A. Then it had, let's see, 1, 2, 3, 4, 5 counties with a grade of B. Then it had 2 counties with a grade of C, and then 1 county with a grade of D. Okay, so, and you can also see the total number of counties in each region by the height, or by the width of that bar graph. Now this looks a little bit different than the other ones, because if you remember, social distancing was missing in 13 of those counties because of the rurality and the low population there. Now this one is my favorite type of graph. So what it does is it takes each distribution of that social distancing variable, and it gets the percentages. So it weights it, it takes the relative frequencies within each group. So then you can easily compare, so that you don't have to worry about trying to figure out how to make your eyes think about the difference in frequency in each region. You can just look at the percentages within each region, and it allows you to see the difference in the social distancing distributions. Okay, so maybe just take a minute and look at that, and just make sure that you kind of understand what's going on there. And if you have a question about that, feel free to jump in there on the chat. So if we were to look for, if we're interested in looking for a relationship between social distancing and region, we would expect there to be a lot of different distributions, right? Because then that would say, well, region 1, maybe they had a lot of grade D proportionally compared to region 5, who had a lot of grade A, which would mean that there's a relationship if there were different distributions being observed in each of these bars. Okay, and this notion of different, right, is all about what statistics is trying to quantify. It's asking that question, is it different enough to be statistically different? You know, and that's where a chi-square test would allow us to test for a difference between social distancing and region. And we're not going to go into depth with that. I don't want to get involved in formulas for this course, but just to kind of talk about holistically, you know, what we would do if we were really wanting to assess that. But one of the reasons why I'm so heavily looking at graphics is that I've noticed over the years that researchers, and myself included, jump so quickly into statistical tests without actually doing what's called exploratory data analysis, and really trying to get a feel for whether you think there's a difference. And then that statistical test should come in and back up what you already think is happening. So you should already be able to be able to get a feel for where you think those differences are. Those tests really kind of just support what you already know is happening. So so that's the relationship between two categorical variables. Let's see here. So I think that maybe we should take a little break. Does that sound right? Does that sound good, Emily? Okay, so let's go ahead and do, if you guys are okay with it, let's do a 5-minute break and get your coffee, go to the restroom, and I'll be here waiting for you. Thanks, everybody.
My cats are really sad to not be part of this today. They usually video bomb me, and I'm like, no, it's a webinar, you can't. They're very upset out there. Oh, they keep jiggling the doorknob.
Oh, that's cute. Do you think I guess we stopped at around 10 o'clock?
Yeah, so I think you're good to go.
Okay. Great. All right, thanks everybody. So we're just gonna keep moving right along with looking at a few more graphical tools and then move on from there. So this was all about categorical data, and I just had a few little points to kind of make for you for, you know, if you have this PowerPoint later on, but we already talked about this, so I'm not gonna spend time on that slide. Now we're gonna move on to quantitative variables. So same data set, just refreshing your memory. So the first one is just something that you really don't see much, but it's called a stem and leaf display. And it's super quick and easy, especially if you're just, you know, at your desk and you want to quickly look at a distribution. You can do it by hand. It's just like it sounds. This is considered to be the stem. And then the last number is going to be the leaf. There's different ways of organizing it if you have different types of numbers. But it's just a quick and dirty way to organize your data. So this is the number of cases by county. So you can see that there are a whole host of, you know, cases that are between 0 and 8. And then, you know, just a handful that are higher up on what we would call the right side of the distribution if you were to turn it on its axis. So just stem and leaf display. Then we have a dot plot, which is one of my favorites. And I use this jitter function in R to make the dots kind of spread out so that you can see them a little bit, but the vertical location of those dots does not mean anything. They're just jittered so that they spread out so that you can see them all. So all this is showing is the number of cases by county, and it just allows you to visually see how, you know, how they're distributed, and then you can compare like the cases per 100,000 to the cases overall. And then on the very bottom plot there, I have the county population size. So you can kind of see some of those as well. So one thing that you'll see on the other scatter plot, like in some cases in a data set like this, like I would really want to label the counties, and you'll see me do that in the next plot just to make more communication, be able to communicate the data a little bit more clearly. So histograms are also a way to display a quantitative variable, and you probably have all seen them before. And in my experience, even people who are around statistics a lot sometimes get a little bit tripped up by histograms, but I just want to remind you what they represent. So if we are looking at this number of cases per 100,000, the graph on the top left, and if we're looking at that first bar that goes from 0 to 50, basically, what this says is that there are, you know, in terms of the number of counties, right, there are approximately like 45, go all the way up there, counties that are between 0 and 50 cases per 100,000. Okay, so it's just a way of binning. So this is much more useful for much bigger data sets. You could see where you would just end up getting a cloud of points for a dot plot. But if you have a lot of observations, say 100,000, a histogram is a perfect thing to use because you can, you know, all you have to do is just scale up the y-axis, and then you can also very easily alter the bin size as well. Okay, and each of these, this is allowing us to see just how unusual some of those unusual points are. Okay, so for the number of cases per 100,000, there's one that goes almost all the way up to 600. Okay, whereas the number of cases raw count went up to around 150. And then again, the population size. So you can see each of these are called what we call right skewed distributions. And I'm going to say more about that with summary statistics in a minute. And if I have this question, if we change this frequency to relative frequency or percentage, the shape of the histogram would not change at all. It would just change how, you know, then it would make, say, this histogram more comparable to, say, another one from another state who maybe had a lot more counties than us. Okay, now we get to the really fun plots, scatter plots, which are my favorite. The first one I'm looking at is just the population size compared with the number of cases. And in my opinion, you know, this is kind of what you would expect, right? As the population size increases, you have this tendency for the number of cases to increase as well, okay? So we would just call this a positive association. Maybe you could fit a line to that, like maybe it's somewhat linear, but then you have this outlier, a clear outlier here. Okay, and this is that Gallatin County there. Okay, so then you can add a third, you know, categorical or identifier variable. You can add it to just some of them if you don't want to cluster up all those labels down here. But this, I feel like, is really important in a situation like this where people want to know, you know, what unique county that really is that they're seeing, you know, that outlier there. Okay, then if we look at the population size and then look at the number of cases per 100,000, then the plot changes quite a bit. It's really interesting how you see this almost like a flattening of that population, or excuse me, of the number of cases per 100,000. Even Gallatin County came down compared to how it was that outlier up here. But then look, Toole County and Golden Valley shot up. Just interesting to observe. You know, this is just purely exploratory, just kind of looking at all the possible relationships just to kind of see what's happening with these data. Then some of you said, well, I want to look at, you know, I want to be able to see like social distancing and, you know, this and number of cases. Well, rightfully so. So we could look at the scatter plot of population size, number of cases per 100,000, and then also do some type of a labeling for the social distancing grades. You know, and a lot of times if you make a plot like this and you separate the colors by, say, gender, you'll see like a very different relationship where there will be clustering. Or maybe you'll separate something by socioeconomic status or some other categorical grouping variable, and you'll notice a definite difference. It's kind of interesting, you know, the only one that I really notice of a pattern is the NAs for the social distancing, because those are the ones that have a really low population for the county, because they weren't able to get those social distancing grades. But, you know, Toole County, you know, I think a lot of groups were talking about this idea that some counties with high counts had mediocre social distancing grades and vice versa. And it could be an issue of time, right? Of when we're actually gathering these data, which time in the month. But just to note, you know, just the different things that are possible. So right now, you know, we're looking at 4 different variables in this graph, which is pretty cool. Then here's another one where we're looking at 3 different quantitative variables all together. So population size on the x-axis, number of cases on the y-axis. So you still see that positive association you saw in that first original plot. But then you have these proportional circles, which are proportional to the number of cases per 100,000. And I was a bad graphical analyst and did not label that here. So, but thankfully I was here to tell you. But I mean, I think that that's a really fun, not fun, given what it's representing, but I feel like it's a really nice graph that allows you to see 3 different variables simultaneously, which is, it's pretty helpful. So I just want to point out, I heard a couple of people talking about looking at the averages by county, which I think is a great idea. But I do caution you against using an average in a case like this where we have a lot of small counts and then like maybe a couple of really big counts. So for example, if we're looking at the number of cases, the median is the middle value of a distribution. Okay, so if I order all of my data values and I take the middle value, that's the median. If I add up all the data values and divide by the total number that there are, that's the mean. So if these are both what we call measures of center, so if the mean and the median are really different, then that's probably not a good thing. So what's going on is that the mean is really sensitive to outliers. So you really have to be careful using that with outliers because it can really be misleading for your data. So if you're taking the average by county the average by region, and you happen to get Toole County in your region, that's just going to inflate the average for that region. So just be careful. I would recommend if it's ever, and if you're ever in a doubt, then just use the median because it's always the middle value. And then you can always tell your reader about these outliers that, or you could report both so they can see that it's inflating that mean. So just be careful with those summary statistics, especially with outliers like we have here. Okay, so so here is a dot plot by region. So it's kind of interesting. We see, you know, region 4 having, you know, a little bit higher overall cases, just like a tendency, right? But there's still a lot of low cases too, but it's like we have some of those higher cases there as well, but not this like drastic overall difference. Okay, and so this is number of cases per 100,000. I have these 5 number summaries down here as well. And what I want to do is just show you really quickly and remind you what a box plot is. So a box plot represents the 5 number summary of a distribution. So the minimum is this lower whisker. This lower line is the 25th percentile. And the middle value is the median. The 75th percentile is the upper side of this box. The maximum is the upper, it's the maximum, but does not account for outliers. And there's a test for outliers that that your any statistical software will do. It's called the 1.5 IQR rule. But this is just a really nice way to display the 5 number summary. And then I'll show you what we love to do with these. It makes it really easy to compare multiple distributions, especially when you have multiple, a lot of observations in each group. Then you can then have a really nice way to make comparisons between those groups. So right now we have the number of cases per 100,000 people separated by Montana state region. Okay. So, you know, we're not seeing a large difference there, although it does seem like there's a slight tendency for region 4 to have a little bit higher number of cases per 100,000 people than the other regions, and region 1 to have the lowest rate. Okay. All right. And then we have some spatial plots, and I am starting to run out of time, and I think that a lot of you kind of understand how to, and we've been looking at a lot of them with just in the media, but I just want to point out that there are different types of spatial plots that are also extremely informative. This one comes from the New York Times, a proportional symbols map. Okay, so it gives you the cases, maps them by the circle, and makes the size proportional to that. Then we also have this one, which I thought was a really well thought out map of coronavirus cases. This is called a choropleth map, which means that we just have these regions that are being shaded according to some either quantitative or categorical value. And it's a little hard to see, but they've added in on the left-hand side confirmed cases, on the right-hand side active cases. Then they shade each region by whether they've had any cases or had any deaths. And then they have this table here. I just thought it was a nice way to summarize the overall picture of what's happening. Thought that was a nice one. And then we have heat maps as well. So this one is just a precipitation map. And so really this is kind of like a pixelated variable that is being mapped as a heat map all over the state. And so these are the types of maps. You can make these in R, but ARC map is the best for making maps, really, in my experience. So there's lots of places that we can go wrong in graphics. Like things like in Excel. I know Excel is quick and dirty for getting different graphics and statistics, and I think that that's great. But you just want to be on the lookout for things like this, where if you have this cone chart where you're not quite sure if the areas are really representing what they're supposed to, and if this cone is supposed to go up to 8 and it doesn't really touch 8, just kind of makes you think, well, why is this 3-dimensional when it really doesn't need to be? Just things like that. You just want to shy away from if it's not adding value to your communication of your data. Okay, same thing goes for this. I mean, it looks like it could be cool, but it's really hard to see. There's no reason for them to be 3-dimensional. There's the green bars for Tom are missing, and it's just hard to make out this overall relationship that they're trying to display. And I think that we could dream up some nice ways to display what they're trying to in that graph in a different way. This one comes from Mother Earth News, and it's super cute. They're trying to talk about different types of foods in a grocery store, and trying to make bar graphs, but it's just a little bit confusing about what's the scale on this. Is this scaled up to 100%? Why is it 3-dimensional? Well, because it's supposed to be a shopping aisle. That's fine. But then these like blue, the blue shading, they should all be in the same order. So all the colors are in different order. So you can't really, with your eye, like really make a decision about what's happening here. So, kudos for the art. And I think that it's a really fine art trying to figure out how to make a graph really pretty, but also really informative. So with that, I am going to try and check my email, because I really want to show you the next graph or the next plot that's coming up, because this gentleman, I guess I have to stop share real quick. But I'm going to tell you a story while I'm multitasking. When I was in grad school, I first saw this, I guess I can't multitask. Desktop. I first saw this gentleman in like a film festival, a mathematics film festival, when I was in grad school, and saw one of these presentations that he gave, and I was just enamored. I just thought he was just so amazing. And I then continued to show his films to my students when I was teaching introductory statistics. And he just passed away a couple of years ago, but he just has a magical way of with data. So or with, and specifically with graphics. So I'm
Just
gonna.
say there's math film festivals.
There definitely is math film festivals.
I love it.
Okay, so I'm hoping, okay, I'm gonna share my screen again. Fingers crossed that this is going to work. Can you hear it?
No.
Oh, that's okay.
Well, do you want me to try playing it on mine and sharing?
That's all right. Let me try one more time.
I have it up on YouTube. Like I can just share YouTube.
Okay, let's do that.
Okay, so holler if you can't hear it. So we'll try this.
Okay.
There we go. So hopefully you can see my screen now.
And then you've got sound off on yours.
Oh,
or you did.
Country bubble show the same.
Yes, it's working.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space with a bit of technical assistance from the crew. So, here we go. First, an axis for health. Life expectancy from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe. And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. The United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh, and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology, and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Well, what you have seen in the last few minutes is a story of 200 countries shown over 200 years and beyond. It involved plotting of 120,000 numbers. Pretty neat, huh?
That's awesome. That was fabulous.
Oh, I'm so glad that you were able to get it to work. Thank you.
Yes, yeah. And the other video you have later, we can do that too.
Great. Perfect. Okay. Well, does anybody have any questions that you want to bring up as we are kind of wrapping up this section of graphical analysis and just like defining variables, those types of things before we move on? Okay. All right. Well, so we are moving right along to, let's see, share my screen again. Okay, so I am just running a little bit behind, so I think I'm going to skip a couple of these. But I basically just wanted you to brainstorm how you would actually organize those data that Hans Rosling just shared with us. So I just want to kind of just point out, you know, he had year, population, lifespan, income, he had continent, and then country. And so this is how I would organize them to where you have, you know, North America continually repeated, right? And this is what would be a time series variable. You have US, you know, continually repeated. Then you have year, which would increase. And with each year, each of these variables is changing, right? But you're gonna have cases where you have variables that are repeating. And some people will just put one in and put like, you know, colons for repeat. And I encourage you not to do that because then your software won't be able to analyze those variables. So just making sure that those are nice and tidy. Okay. And then as we move on, we're going to start talking about how we actually can work to collect data that are representative of our population and thinking about biases. So I'm going to skip over this next slide here. And now we're moving into this section on just really starting to think about how we would want to be able to produce our own data. So as epidemiologists or teachers or you know, any field that we're in, a lot of times we're just given a data set, but sometimes we are able to actually design studies. And even if we're not able to do that, I think it's worth thinking about what makes a good study so that you're able to critique different literature and then also be able to better understand the data that you're working with as well. So the first thing that is one of the most important things you need to do when you're starting to think about collecting data is formulating a research question. So, you know, we wouldn't build a house without precise construction plans. We shouldn't just go out and start collecting data without really thinking about what we are really interested in learning, what we're interested in studying, because that can be really expensive, data, collecting data, managing it, all of those things. So we really want to, you know, hone in on what our question really is. So let's say that I want to know, does adherence to a Mediterranean diet prevent heart disease? Well, I need to be a little bit more clear than just that. Like, who am I trying to actually learn about? Is it all age groups? Is it only females? Is it only people over 60? You know, who am I actually trying to learn about in terms of this Mediterranean diet? Because I can't just take on the whole population. Where am I going to focus? Are they going to be Americans? Are they going to, you know, live all over the world? Where are they going to be located? What's their gender, etc.? And then how am I going to actually define Mediterranean diet? How am I going to define what prevent heart disease really means? These are all questions that I need to be prepared to answer, and it takes a lot of time to hone in on acceptable ways to define some of these things that we're collecting. Okay, so a task for you, if you can randomly choose a number between 1 and 4, and then choose the corresponding letter, that would be lovely.
Got almost all of you. Almost. Looks like we're missing 2 people. Are they in here? They wander off. Okay, I think that's what we'll get.
Okay,
22.
we're good. Okay.
Okay.
Okay, so if this is just a test to see if we were able to perfectly randomly choose a number between 1 and 4 as humans, then we would expect to see an equal distribution of 1, 2, 3, and 4 on that, or A, B, C, and D on that graph. And there's by chance that it would have a little fluctuation. That's kind of what we talk about in randomness and probability, that it could differ a little bit. But I'll say that in all the years that I've done this question, with thousands of students, the higher proportion is always on the 3. Everyone always loves the 3. And so this question, this poll, is just to get you to think about that as humans, even though we think we're trying to randomly choose something, just as humans being who we are inherently not random. Like, even if you try and, choose random points on a plot, you try to actively get good spacing, and so you're inherently not random. You don't have the ability to incorporate randomness. So we have to rely on other ways to incorporate randomness into our studies. So the reason why we need randomness is there's so many ways in statistics that we need it. We can utilize it in sampling to help us choose a random sample, experimental design to figure out who is going to get which treatment, so that we don't, accidentally, if we're letting people choose their own treatment, then it kind of defeats the purpose of doing an experiment. We're using randomness and statistical inference, which I'll talk about, as well as simulation studies. In general, whenever possible, to protect yourself from biasing data collection, try to incorporate randomness. So this, I encourage you all, even right now, to go to random.org. And this is it's a site that's free, and it's run by a university in Ireland. And they have somehow created these random numbers through atmospheric noise. So you click on this button, and it sends this signal to Ireland and has it generate some numbers for you in Ireland and sends them back to you. And you can put lists in there, and it'll randomize them for you. That's how I did all the randomization for this. And you can randomize things in R as well. But if you're looking for a quick and fun thing to do, you can go to random.org and check it out. So right now I'm gonna switch to, we're going into this data collection phase, and we're gonna start on sampling. So I'm gonna just talk to you about 3 sampling plans, and then move on from there. So let's, for the sake of the next few slides, pretend like all of these shapes are a population you want to learn about. So maybe they're all people, and the shapes represent different features about those people. Okay, so maybe they're, you know, different socioeconomic statuses or anything that's pertinent to your research. So we in general want to know something about this whole population. But in general, taking a census is not a good idea. It's really expensive. It's prone to error. There's a lot of reasons why we try to stay away from using census processes. But what we can do is we can take a random sample. Okay, so one way I could do that is take all of these people, put them into a list, and use random.org to shuffle them up for me and take the first, if I want, there are 60 people in this plot. If I want to take a sample of 10 of them, then I can randomize the list in random.org or R or SPSS. They all have random sampling abilities. And I am able to randomly sample who I'm getting in my sample. Now, in the population, I just want to share these population quantities down here. There's 50% pluses, 33% circles, and 16% stars. Those are population quantities. They're called parameters. In the sample, we got 60% pluses, 30% circles, and 10% stars. So 60 versus 50, 30 versus 33, and 10 versus 16. So for a sample of size 10, I'd say, yeah, it's probably about right. Okay. But one of the most fundamental thoughts or ideas of statistics is on this slide. First of all, you know, we're trying to estimate, or we're trying to learn about a population parameter, say the proportion of pluses in this whole population. And we do that by taking a sample and computing a statistic. Okay, and in practice, we only compute a single statistic, but in general, we want to know, well, if I did take another sample, how much would that change from sample to sample? And so I just conducted a little simulation for you so you could see how much variability there is when I'm taking a sample of size 10 from this population. So in the first simulation, I got 6 pluses. The second simulation, I got 6 pluses. Remember that the true population proportion is 50%. Then I got a 5, a 7, an 8, a 5, a 3, a 4, a 4, a 3, a 5, 8, 4, 6, 7, 3, 3, 7, 3, 5. So it's definitely fluctuating, ranging from 3 all the way up to 8. Okay, well, I can use my trusty little graphical technique of a dot plot that we just learned and kind of visualize that. Okay, well, all of those different sample proportions, you know, they're fluctuating and they seem to be centered at around 0.5. Okay, well, the notion that these sample proportions, if I repeatedly take samples of size 10 from the population, this is an extremely important concept. This is called sampling variability. In practice, I only take 1 sample, but if I could continually take samples of size 10, this is how much variability is happening in those sample proportions from sample to sample, okay? And if I do that, conduct that simulation 200 times and make a little dot plot, you can kind of see what's starting to happen, okay? And you can, there is a really nice sample simulator here that I put a link on that you can look at. and you can simulate these different sample sizes, simulation numbers, and you can see how the sampling distribution is created. And this is just for, this is just for our understanding of sampling variability that we create these sampling distributions. But this website here is a really nice way. It has a dynamic tool where you can look at the different distributions for different sample sizes and different population proportions. And it allows you to really understand how sample size is related to variability. So what this is really displaying is called the central limit theorem, and it's one of the fundamental theorems in statistics. So notice that this distribution of these sample proportions is pretty symmetric and mountain shaped. It's centered at the true population proportion. So those two features are part of the central limit theorem. And it turns out that as the sample size increases, that sampling variability gets smaller and smaller. And it's always going to be approximately what we call normally distributed. So here is the main result of the central limit theorem. And we use this a lot when we are computing p-values and constructing confidence intervals. But I think that it's really a hard concept to just really conceptualize what a sampling distribution is, which is why I wanted to present it to you here. We don't have time to go through all of the different theorems and precisely how to quantify them, but I think just understanding this idea of a sampling distribution helps you understand what a confidence interval represents and what a p-value represents. Okay, so back to the sampling problem. If you notice, like, what can happen just by chance is that we can still, even though we did collect this random sample, we can still not cover some of the population. So if this is a spatial plot, I'm missing all of these people down here. There's not a sample that happened down here. And look, something's happening where for some reason the stars are living up here. So it's like I'm getting under coverage down here. So, so that's just something to think about. And what we can do, if we know we have some geographic locations for these plots or these people, then we can maybe separate them into, for example, regions like we did for Montana, and make sure that we get representation from each group. So this is called a stratified random sample, and the randomness comes that we would still take a random sample within each stratum. So for example, that something would look like that, to where we get a sample from each stratum. Then we also can have a systematic random sample, and these can be extremely useful when you maybe don't have a list of people to sample from. And if you can just randomize who you start with, you can say, okay, since I need to sample 10 people from 60, I can just randomly choose one of the first 6 to start with. In this case, I chose the second one. And then I can say, okay, I'm going to go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and so on. And I get a really nice coverage on my grid there. I still have incorporated randomness to minimize the chance that I've incorporated bias into my sample. And a lot of times that systematic sampling can give you some really nice coverage in a sampling plan. Okay, so let's look at a sampling example. So realistically, we're not gonna always be able to know who's in our whole population, or we might not have access to our whole population. Okay, so here's an example. And I also wanted to show this just based on the headline. to encourage you to dig a little deeper when you're reading these headlines. So this headline says, in the US, 14% with likely COVID-19 to avoid care due to cost. So they're suggesting that 14% of people in the US who have COVID-19 would avoid care due to cost. And you might read that statement differently. And so I just think it's good to actually dig in deeper and actually look at their documentation for how they conducted their sample and what their question wording really was. So let's dig a little deeper. And this is a little hard to see, but it says, if you or a family member had a fever and a dry cough, would you avoid seeking treatment due to concerns about the cost of care? Okay, and that's the 14% right there. So that's the question that they're citing on their page, is if you or a family member have a fever and dry cough, would you avoid seeking treatment due to concerns about cost of care? So to me, when they're advertising, I mean, I don't think they're trying to be misleading, but when they're saying that 14% with likely COVID-19 will avoid care due to cost, and then I read that question, and that's where that 14% is coming from, I'm just wondering to myself if I really think that that's a valid statement that they have. But then the second question does say, if you thought you would be infected by the coronavirus, would you avoid seeking treatment? And that percentage is 9%. But, just reading that precisely how they ask the question can really help you determine how you're interpreting those data. But also think about, how are they actually getting this percentage? Well, they're having to make phone calls to people, and maybe this blue square or this gray square is all all people in the US, for example, okay, in this blue square. Okay, but it turns out that when we make phone calls to people in, either with or without a cell phone, they used some different quota sampling methods, which we'll talk about. But it turns out that you might not even have the chance of selecting some people. And then you might actually include people who you didn't want to include in your population of interest. So a sampling frame, the definition of a sampling frame is the group of people who actually have the chance of getting selected. And when the sampling frame is very different from the population, that's when you can have big problems. Okay, that's when you get these historical stories of elections being completely miscalculated and predicted incorrectly when they've completely gotten the wrong sampling frame. So your goal is to get the sampling frame as close to the population as possible. So what Gallup does, they took a sample of 1,000 people, and they obtained a minimum quota of 70% cell phones, 30% landlines, to try and make sure there's forcing representation there. So that's kind of similar to a stratified sample. And then they're calling and asking those questions. So they're gonna probably most likely get a lot of non-response. And so we just wanna be thinking about that when we're interpreting how these results are affecting our perspective. Okay. So let's see here. So I think I might actually pass on this one. I was trying to kind of quantify sampling variability for you, and I think I did that with those dot plots. Just really quickly, these are two different sampling distributions, one for a sample of size 500 and one for a sample of size 1017, like they did in the Gallup poll. So what I was trying to illustrate to you here is that the sampling distribution for the sample size of 1,000 has less variability than the distribution for the sample size of 500. Okay, and this is really what we're getting at when we talk about how big of a sample do I need if I want to get a confidence level of this and a margin error of this. Okay, it's all based on the central limit theorem and how much sampling variability there is in the sample proportion in repeated sampling. So, you know, once I start to get, if I have a sample size of 1,000, if I get to a sample size of 3,000, I start not to get as much feed or as much reward for upping that sample size. And so I end up sometimes not reaping the benefits. So Gallup tends to do samples of around 1,000. That gives them a margin of error of approximately 2% for a 95% confidence interval. And that's what they're shooting for. So that's generally the sample size that they go for. So just think about bias. There are different ways to incorporate bias into a sample. So there's selection bias. So some people might be more or less likely to be included in a sample, such as with telephones if they're not answering their phone. Your data can be biased by even just the question ordering, the order in which someone reads those questions. If it's a really sensitive topic in a survey, that can introduce bias into your sample if someone is unlikely to give a truthful answer. And then there's non-response bias is a huge problem because a lot of people won't return mail surveys, won't answer the phone. And the issue there is not the sample size, but that what if all those people who aren't responding, what if there's something very similar about those people, and then you're not being able to get them represented in your sample, and that's really the problem. Okay, so just think about this when you're getting your statistics, what we're really going for. So we have bias, and we have no bias, and then we have precision, and we have imprecision. So what our goal is to be very precise when we're getting a sample, meaning that, you know, we have low sampling variability, we're very precise, we don't have much room for error, not much margin of error, and no bias, meaning like we got a representative sample, nothing seems to be systematically different from the population of interest, so there's not a bias in our sampling. Now, you could sample 10,000 people and have a biased sample and it's useless, right? Because even though it's very precise, you're way off the mark. You haven't hit you haven't hit the bullseye. And so, you can't overcome a bad sampling plan by just like throwing money at a problem and sampling more people. So you just really have to make sure that you have a good plan and make sure that it's both no bias and high precision. So you can also have imprecision and no bias, which I would actually probably prefer, because at least I'm still centered at that true value. And then you can also have the worst case scenario where you have imprecision and bias as well. So I feel like that's a really nice graphic to get you thinking about, what we're trying to manage when we're dealing with sample size and our strategy with sampling. Okay, so I know it's getting close to lunchtime, so I thought I would make your stomachs grumble with a really good example. So in general, the larger the sample size, the less variability you have in your sampling distribution, which is a good thing, right? The bigger the sample, basically, as long as it's unbiased, right? You have more confidence in your sample, you have less sampling variability, it's more precise. Okay, therefore, you can have a smaller margin of error in your confidence interval. but it does not mean that a larger sample will produce a more accurate statistic based on last slide. So just be careful with that. I already hit that one home. But here's a common misconception that, and it's really easy to fall into the trap. A lot of people think that if I have a bigger population size, I must need a bigger sample. So let's say I'm taking a random sample from all Montana residents of 1,000 people. Well, if I'm going to sample all of the United States, then I must need a bigger sample, right? No, it's not actually true. The sample size, you still determine your sample size based on the margin of error you're willing to accept, and your confidence level. Those are really the only two things. And I know that I'm speaking in those terms are maybe not familiar, but this idea that you have to for some reason take a larger sample is illustrated with these vats of soup. So think of these two big pots of soup, giant vats of soup in this big restaurant where it can produce bowls and bowls of soup. And in this little pan, we have the exact same soup, okay, but it's just a small pan. In order to be able to taste that soup and decide if it tastes okay, I still probably only need a spoonful from each one. And that's the whole rationale behind you don't need a bigger sample size with a bigger population. Because all you need to do is taste it to understand how it tastes, right? Just because you're sampling it from a big vat doesn't mean you need to eat a whole bowl to sample it. You still just need the spoonful in order to taste that it's, you know, the carrots are done, you've got the salt in there, all the things are mixed up. Okay, so that sample size really is not affected by the population size. Okay, great. So in summary, the big overarching goal with sampling is that we are trying to learn about a big population by taking a representative sample from that population. And we want to put all measures in practice as much as possible to make sure that we get an unbiased sample so that we're not systematically missing a facet of the population when we're getting that sample, okay? Emily, what do you think about break, or do you think we should keep going? What are your thoughts? Oh, you're muted, sorry.
I should know it better than that. We can take a break whenever. When was our last one?
I think it was around 10.
Oh gosh, was it? We're flying. Yeah, we can definitely do another little break.
Okay. Is everybody okay with just a 5 minutes so that I can just pack it in for the last?
Sounds good.
Thank you.
Got David's blessing. So. I loved that video.
Oh, I'm so glad. I love that one too.
That was really cool. I'm going to show that to my brother later.
Oh, good.
And I have your other video up on YouTube as well. So when we get to it.
Awesome. Thank you. Thank you. That's excellent.
It supposedly smells really nice out, so I'm going to open my window.
Oh, because of all the blossom trees?
Uh-huh.
Nice.
We have apricot trees, which were amazing, and my neighbor has 4 apple trees, so it's very perfumey.
That sounds lovely. My daughter just picked a bunch of lilacs and apple blossoms and brought them into the house, and just like, just so happy.
Ah, that's I had a bunch of friends and such have birthdays recently, so I kept going to my neighbor's house, and he let me cut little like short limbs off, so everyone just got apple blossoms.
Perfect.
Yep.
That's great.
Apple blossoms mean apples, though, and as a kid growing up with trees, that was my job to pick up all that fell. So that's not as much fun.
That's what my husband said. He's like, this is the only week that I like that tree.
Yep, and it just gets messy. I'm pretty new to the whole statistics thing. Obviously, I know a bunch of you that do it, but I don't have much experience. And man, thinking back that again, when I was getting my chemistry degree, it was all calculus, which was great, but like, this would have been really handy. I feel like I've used this kind of stuff a lot more than I do, you know, calculus. So.
Right. Yeah, I mean, I think that it's, well, like that, like, I'm forgetting the gentleman's name from that TED Talk. You know, he was just making that point, you know, calculus is extremely important, and you use it in statistics too, but, you know, like if you're trying to get that like hole-in-one class that everyone will most likely use at some point, you know.
Oh my gosh, I think of all of the studies I've been part of, and thankfully we've had statisticians to assist, but oh, I could have done my data so much nicer. I know now for next time. Have you worked with Ethan Walker much or at all?
A little bit, you know, we started doing like a running club together. Yeah. So I got to know him through that. And then I was actually trying to get him, he got it to me late last night, and I just didn't have the energy to pull it in. He was working on getting me case by case COVID data.
Woo!
And he told me I couldn't like share the actual like raw data, but that I could make graphs. And I made some, and they, you know, I didn't, in the end, it didn't seem like it was worth like adding more graphs. But yeah, he seems like such a neat and really great guy.
He's awesome, and I know he's picking through all the data from my kids' air study.
Oh yeah.
There's a lot of data there, and again, it's amazing the things where I'm like, I could have probably done this a little differently to make it easier for the poor guy who's now trying to make sense of it all.
Oh, it's just the nature of the process, I think, you know.
It's been fun to see graphs and stuff though, just because I did field work, and so you just go and you collect info, but to actually see what the heck it means has been really, really cool. So.
Oh yeah. Oh, that's neat.
Yeah.
Cindy, I was curious if you viewed Dr. Christensen's webinar last Wednesday out of Missoula. Did you happen to see that?
I did. I watched some of it. I wasn't able to get it live, but I did watch a recording of some of it. Yeah. That was good.
He
Were
said
you
that,
able to do, you were
yeah,
there?
yes, I did. And I was, again, we're going to have data explosion. He said there are over 1,200 COVID studies underway.
Wow.
And that's something that, the publications were coming out daily. So I think we're going to be able to digest lots and lots and lots and see all kinds of presentations and types of analysis.
Mm-hmm. Yeah, absolutely. Yeah, the one that was really interesting to me, I briefly showed it because the work that I do a lot is with air pollution, and there's that one that they're showing a pretty significant association with the particulate matter and deaths from COVID.
That's fascinating. I need to look more into that.
Mm-hmm.
Well, I think once we understood that air pollution wasn't just a respiratory problem, but a systemic problem, is that we significantly impact the organism and their overall resistance to other things. So COVID is another one of those stressors that's just taken advantage of that.
Mm-hmm. Yep, for sure. Well, should we mosey back on?
Go for it.
Okay. Okay, so we have about 50 minutes left, and so I'm going to try and talk a little bit about studies, making associations between explanatory and response variables in two different types of studies, and then transition to statistical inference. And I think these are both really important, and I'm going to try and split the time equally. But again, please feel free to stop me if you have any questions, and I'm definitely happy to stay for questions after or through email correspondence as well. So observational studies and experiments. So public health researchers often want to study relationships between two or more variables, such as, does smoking cause lung cancer? Do higher levels of air pollution cause a higher death rate in people infected with COVID-19? Can diet reduce the likelihood of coronary heart disease? So each of these questions is studied with an explanatory or exposure variable, and epidemiologists tend to use this term exposure variable, and then the response variable is sometimes also called the outcome variable, but those are interchangeable as well. But exposure and outcome seem to be more heavily used in public health. So the first thing, observational studies, the researchers simply observes the participants as they are. There's no manipulation. So smoking and lung cancer studies on humans are always observational, right? We simply observe whether a person smokes and record whether or not they develop lung cancer. Or maybe we're interested in comparing the language development of young children who attend a large versus a small daycare. Okay, so in the explanatory and response variables in the above, I would say if I'm looking at does smoking affect lung cancer, then the explanatory variable would be smoking, the response variable would be lung cancer. Maybe they're both binary. Maybe smoking is like number of cigarettes, average number of cigarettes per day, or average number of packs per day, something like that. So it could be, or it could be something like some type of like categorical assessment of how big of a smoker they are, like a lot, smoke a lot, little, something like that. For the explanatory and response of the daycare example, then we would have, whether we would have daycare, large, small, that's a binary variable, is the explanatory. The response would be some measurement of their language development. So does daycare, large or small, affect language development, which is the response? Okay. So I was reading, in my little, following the wormhole things with this presentation, I found this paper that someone did a lit review of hundreds of public health articles and then did a random sample of some of them as well. And this is Hyatt et al. In 2017, and I'll provide you with all the literature for these things that I'm citing. But they said that approximately 82% of public health research papers are based on observational studies. So I thought that was quite interesting, but it does make sense that a lot of the things we're interested in studying don't allow us to actually manipulate the subjects that we're studying, which I'm going to talk about on the next slide and explain why we generally can't manipulate. So in an experiment, the researcher actually assigns the value of the explanatory variable to each unit. Since the researcher assigns the subject to treatments, then we can actually establish a cause and effect relationship. And that is the main reason why experiments are used, because we can say, hey, we randomly assigned, you know, these people to this treatment, these people to this treatment. That, therefore, the only systematic difference between them is the treatment itself. And therefore, if we saw a large difference in treatment versus no treatment, it must have been the treatment that caused that difference. So here's an example. We have 7,447 participants in this large study that I'll say more about and cite later in a couple of slides. They randomly assigned these people to one of 3 diets. All of these people had high cardiovascular risk, and they were either asked to adhere to a Mediterranean diet supplemented with olive oil, Mediterranean diet supplemented with nuts, or a control diet. And this is with reduced fat. And this was, I have it, the date cited, I think it was like 2006. So it was really when these high fat diets were really kind of coming on the scene and wanting to figure out if they could reduce heart disease. So why do we need an experiment? Why do I say a cause and effect relationship can be established? It's because of confounding variables. So if I tell you that if you can just start having your country eat more chocolate, you can therefore produce more Nobel laureates per 10 million in the population, right? There's a strong correlation here, 0.791 with a very small p-value. There's a strong correlation here between chocolate consumption and Nobel laureates. Okay, I don't know what else could be describing this relationship, but I don't quite feel comfortable saying that chocolate consumption is causing these Nobel laureate counts to go up. Maybe there's some association or some third variable there that's actually explaining that relationship, right? That's kind of what a confounding variable is. You don't know for sure if the difference you're seeing is actually because of that explanatory variable. That's the whole reason why those observational studies need some more work in order to be able to make these conclusions from. Here's another one, number of TVs per 1,000 people. These are all countries that each dot represents a country. Life expectancy on the y-axis. So it seems like, so the number of TVs per 1,000 people. So as the number of TVs increases, life expectancy increases. So let's start sending these countries televisions, because it will cause their life expectancy to go up, right? So another idea of, like, we see this strong association between these two variables. It does not mean that one is causing the other. And likely something dealing with socioeconomic status, you know, access to healthcare, all of these other things that are most likely actually contributing to the differences in life expectancy. So basically, these are just some bullets that go through what I just said. The whole reason why we need experiments is so that the only systematic difference between the treatment, say the treatment and placebo or the treatment groups, is the variable itself. There's nothing else that could be explaining what you're seeing. Okay, so you can't let people kind of choose what group they're in because of this worry that they could be in, there could be a confounding variable there. So this is the article that produced this study, this primary, and it was actually, so it was from the New England Journal of Medicine, and they came up with some pretty clear results showing that this olive oil diet combined with nuts reduced these coronary heart events, basically. But check out this thing at the top of the, so I used to show this article because it's 2013, I think I said earlier, but 2013, I showed this article in my class quite a few times, and I just looked it up for this class, and it says this article has been retracted. So I looked it up, and I guess there was some controversy about the fact that some people were not actually randomized into the groups. So they still got the results that they obtained, but something came up where they realized that some people weren't truly randomized into their groups, that they chose which group they were in. And so they completely retracted the results that they got, just because it's no longer an experiment. It's now an observational study, right? And so now they can't, without a doubt, say that it was the combination of nuts and olive oil. It could be their lifestyle. It could be some other confounding variable. I just thought that was fascinating, especially in light of the topic that we're covering. So I left it in there because I thought it was pretty cool. Okay, so I find that to diagram these really helps me understand what's happening. Super simple, but I just feel like it helps get me kind of up to speed on all of the rhetoric, gets me to just visualize what's happening. So I go from left to right. I start with these subjects, 7,000 subjects. Okay, these arrows, notice that I draw a line across them to denote those were randomly assigned. Okay, and that is the thing that defines it as an experiment, is that random assignment to the treatments. So we have 3 treatments, and then and you could have another set of treatments as well. Like maybe you want to do diet and then randomly assign them to exercise regimens. So that would be another variable. That would be what is called a factorial design. So, you know, you can play around with this. You can also have a blocking variable where maybe you first separate people into age groups to make sure they're very evenly assigned to the different treatments. But usually, especially in a group this big, the randomization will take care of a lot of those differences, so you don't have to worry about the blocking. Okay, so the main components of an experiment: random assignment, then we have our exposure variable, and then we compare. We need at least 2 groups to compare. So if we just give them all Mediterranean plus nuts, like how are we going to assess that, right? We have to have a comparison group. So you always have to have at least 2 groups in your experiment. So here is the observational study for smoking. We have subjects, but we can't assign them to smoke and not to smoke, right? And that's really the whole crux of a lot of public health studies, is that we can't conduct, we can't conduct these studies where we're exposing people to these exposure variables that could be detrimental to their health. And so that's why, that paper, I'm guessing that's why, some 80% of these public health papers are based on observational studies. And they're much harder to conduct, much more expensive, all of those things as well. This next slide was put together by a colleague of mine that I used to teach with, or who I used to teach with. And I just love how it really just kind of explains all of the mysteries to me in a very succinct way, especially for us in public health who are dealing with mostly observational studies. Well, how can we move to establish cause and effect if we can't conduct if we can't conduct experiments, how can we even hope to link smoking and lung cancer? Well, here's the answer. So we did conclude kind of as a, conclusively as a country that smoking does in fact cause lung cancer. And the reason is that we had all of these supporting mechanisms coming together. So it wasn't just one thing. It wasn't just an observational study. It was a lot of different things. This consistency of association across many studies, both prospective, meaning you follow them into the future, and retrospective, meaning you look at the people who got lung cancer and go back into their history to see what they had done in the past. How strong is the association? Is it just weak or is it really definitive? This existence of a dose response. So the more somebody smoked, the more likely they were to get lung cancer. The existence of a temporal relationship. So this cause, smoking, almost always precedes the effect, which is lung cancer. So that's really important too, this temporal component. Supporting evidence from controlled experiments with animals. So these animal studies can really help kind of just help us tweak out some of the differences that we're already seeing in the other studies. And then number 5 can also help establish number 6, which is a plausible mechanism, which is established from biochemical studies. So I just thought that was a nice reminder that, not all is lost with observational studies. They still give us a lot of information. We can still make very strong conclusions, but we just have to be really careful that those confounding variables are very important to consider. So just to keep that in mind. Okay, are you ready for your quiz? Check this one out. It's a test of roughly 200 men and women. And so tell me what type of study this one is.
They're trickling in.
Can you resend the choices? I dropped mine down so I could read it, and now I don't know where it is.
Oh. I can't redo it at the moment. I'm sorry.
Not a big deal.
It went away. All right, we got 15 of you. Oh, there's 16. Wait a little bit longer.
There might be at the bottom of your screen, Dave, a choice, an icon that says polling, that you can make it big again.
Thank you.
Nice. Okay. Oh, we're still getting a few. We got 18. Let's see if everyone who's present isn't wrangling kids or something. Okay, we'll end it and I'll show you results.
Great. All right, thank you everybody. So, a majority of you are correct. It is an observational study, but let's just talk about it real quickly. So it said that those with moderately high blood pressure, so blood pressure would then be the explanatory variable, did worse on tests of memory and reaction. So memory and reaction would be a test. And so I think what can be a little bit confusing when we say that experiments like actively or manipulate somebody, when you talk about tests of memory or testing somebody, then it can sometimes feel like that's manipulating, but that's still just a measurement. So just remember that an experiment is when you're actively giving them some type of level or variable, and that is the, not the variable, but the levels of the variable, and it's specifically for the explanatory variable. But nice job, thank you. So I'm sure that you all have heard the term placebo, and I'm sure you've heard the term blindness, but just so you know that placebo is, you know, it doesn't have to just be like that placebo pill. We can have a placebo group who does not get the treatment. You know, like in the polio example, where with Jonas Salk, they had actual placebo vaccines for that placebo, for that test that they did. And so here's the gold standard in experiments: randomization of subjects to treatments, just like we talked about, making sure that we manage extra sources of variation, such as making sure everybody gets the same, you know, set of nuts every day, or whatever it is, like making sure that you're trying to get everyone the same exact treatment that they're supposed to get. Multiple subjects in each treatment. This is known as replication. So if you don't have that, you can't quantify your differences. So you have to have, and you know, you can do different power assessments and sample size assessments to figure out just how many you need based on what kind of tests you're going to be doing. And you need to have at least 2 treatment groups for that. Oh yeah, sorry, I just said that. Incorporating the placebo group. And then blindness. That can be a really important one to include, so that if a subject, well, of course, if they're getting a placebo, they should be blind that they're getting the placebo, right? Because that's the whole point. But the researchers can also be blind, and that can really help if there are any, you know, anything that requires judgment on the researcher's part when they're actually assessing these people for improvement. That can be a really important piece in those. Okay, now here's the crux. Can we use random sampling in experiments? So this is a really interesting question, because almost never, like it's hard enough to get people to participate in your experiment, let alone trying to go out and randomly sample someone and tell them that they need to be part of your experiment, right? And so you've got this randomized experiment, but yet you still want that group of people to be representative of some population you're trying to represent. That can just be, it can be tough. So that's just something to consider when you're both assessing experiments and trying to design one. Is that if you're experimenting on 20-year-old college boys, right, you can't be making inferences on 60-year-old people, right? You have to be clear about what your scope of inference is going to be. Okay. So now that we know a little bit more about studies, I just want to briefly revisit Florence Nightingale. So she basically was just collecting data. She wasn't necessarily actually conducting some type of a study. She was just really more of like sampling and making observations, which there wasn't really like an explanatory and response variable, unless actually she was looking at sanitation conditions and deaths. So that is an observational study. A lot of researchers fought very hard to make the polio vaccination trial a placebo-controlled experiment. So it turns out that in the beginning, they were going to all just do, second graders were going to get the vaccine, and they were just going to observe first and third graders all across the country. But only second graders were going to get a vaccine. And some researchers fought very hard, and some counties had already signed on to the voluntary study. And so they still followed through with that plan. But they were able to convince other counties to sign on for this randomized controlled placebo experiment. And Montana was one of them that participated in the controlled experiment. And in the end, they did notice a difference in the results, that randomized controlled study versus the voluntary study. They actually noticed that families that were coming from a higher socioeconomic status were more likely to sign on to the voluntary study, but they were actually also more likely to get polio. So it was kind of this confounder there, because of they think maybe because of sanitation purposes. I don't know a lot about that, so I can't claim that to be extremely accurate, but that's along the lines of what it was. Let's see, and so we have other studies that we've talked about that also talk about this observational and experimental design. Okay, so now I think Emily is going to show this video for me. And this is going to be the last video, and I'm going to use this to illustrate the idea of statistical inference.
I can't hear it, Emily.
Such a sensitive nose.
Oh, got it.
Flowers, fumes, coffee. For most of us, smells are simply part of everyday life. Not for Joy Mill. Oh, thank you. This grandmother from Scotland has such a sensitive nose, she can smell disease. An incredible ability, verified and published in scientific journals, where she's known as the super smeller.
There's somewhere between a dog and a human. And I take that as a compliment.
Joy, a nurse, says she's always smelled changes in her patients, but it was a change in her husband Les, a doctor, that would alter both of their lives.
He was only 31, just going on 32. It was that summer.
Les didn't smell like himself, and the odor wouldn't go away.
I thought, well, I'm not going to nag about this.
More than a decade later, at 45, Les was diagnosed with Parkinson's, the disease actor Michael J. Fox has battled for years. Muhammad Ali had it too. It causes tremors and eventually dementia. At Les's very first support group meeting, Joy's nose was overwhelmed.
I said, look, everybody else in that room with Parkinson's has the same smell as you. And he just went, what? What on earth are you talking about?
University of Manchester biotechnology professor Perdita Barron was skeptical. So she and a team of researchers tested Joy, not with high-tech machines, but T-shirts.
Well, we got some people with Parkinson's, 6 people, and 6 people who didn't have Parkinson's, and we bought them identical T-shirts, and they wore them overnight.
They gave the shirts to Joy, and she sniffed out all of the Parkinson's patients, plus 1 T-shirt in the control group. 9 months later, that person was told he had Parkinson's.
That was really transformative. Now, some other person had it before they were clinically diagnosed.
Once symptoms like tremors start, the damage to the brain is already irreversible. Joy could be the key to catching it early.
So what does Parkinson's smell like?
It's a very musky, thick, greasy odor. It's not pleasant.
But a lot of scents make her smile. She tried to teach me how to really stop and smell the flowers.
I can definitely smell the floral on the blossom.
Never just smell once, because smells are not one smell.
Now you're smelling
the chlorophyll, the basic molecules.
Molecule.
Yes.
She smells molecules from people, too.
That's the cardboard smell.
With Joy's help, researchers pinpointed the Parkinson's smell to sebum, the oily substance in the skin, and identified molecules specific to the disease. The result, a groundbreaking new test.
We can tell within about half an hour from a patient sample, just a swab, whether someone has Parkinson's or not.
That test is still in early trials, but if it works, it could save countless families from the pain Joy and Les went through. He died 4 years ago.
What do you think he
would think about what's happening?
I keep on saying to people who ask me that, it's the tearjerker. No, he would be just over the moon.
An extraordinary ability that one day might lead to a cure.
That was awesome.
Thank you. Thanks for doing that. Okay, so now I share mine again. Okay. Can you see and hear me and everything? Okay, so Joy Milne, based on that story, I think it's a really nice way to just learn a little bit about, you know, just her story, but then also talk about, it's a great intro to hypothesis testing. And this is a hard, I don't know everyone's just like level of comfort with p-values, but in general, I feel like we can always use a little brush up. So, so I thought we would just start pretty small and just talk about, you know, we in the hypothesis test, we have a null and alternative hypothesis. The null hypothesis represents the status quo, like nothing's changed, nothing's unusual. The alternative hypothesis is the theory that we're testing. So let's, for Joy Milne, let's let P be the long run proportion of times that she could correctly identify the disease status of a person or a t-shirt, right? And so the null hypothesis would be that she's just guessing. If she's just guessing every time she sees somebody or you know, grabs a t-shirt, then on average, she would be right 50% of the time because she would just say yes or no. So if she has the ability to determine which of these t-shirts belongs to someone with Parkinson's disease, then the proportion of time she is correct will be significantly greater than 0.5. Okay, so that's the basic test. And you know, in other tests, you could even say, well, I want to test to make sure it's more than that. I want to test to make sure it's more than 0.8 or something like that. But, you know, for this problem of is she just guessing or is she doing better than just guessing, these would be the null and alternative hypotheses. So recall that she was given 12 t-shirts and she correctly identified the disease status in all 12. What's the chance that she could have done that when she was just guessing? So we have a statistical model that can help us analyze or figure that out, or we can just use our basic probability skills to figure that out. I'm going to show you a way that we can use statistics and randomness to kind of tackle a problem when we don't know how to approach it. And it's with simulation. It's one of my favorite ways to study probability when I don't understand how to solve a problem. I just simulate it so I can at least get a handle on it. So basically, let's assume that Joy is just guessing and figure out how much variability there is in the number of correct identifications using, you know, random.org. You can go in there and say, you know, flip a coin 12 times for me, basically, and figure out how many, you know, how many heads I get. That's pretty much exactly what we're doing here. So I did 50 trials of this. And so the count that you see here is the number of correct identifications when she's just guessing. Does that make sense? Number of correct guesses or identifications when she's just guessing. So here she got 8 correct. Here she got 6, 8, 5, 6, 7, 4, 2, 7, 4, 8. I don't see anything above 8. Okay, so that means when we observed a 12, that was pretty darn unlikely. Out of 50 times I ran that simulation, not one even went above 8. So I'm pretty convinced that that's something unusual is happening, that she's probably not just guessing. Does that make sense? because after all of those replications that I just created, it never even came close to 12, okay? So that's what a p-value is going to assess. It says, if the null hypothesis is true, okay, the same thing in Joy's case, if she's just guessing, okay, if the null hypothesis is true, then the chance that we could observe what we did is so unlikely that the alternative hypothesis must be true. So it's a very small p-value is going to give us very strong evidence in favor of the alternative hypothesis. So the p-value is the probability that Joy could have gotten 12 correct if she was just guessing. Well, based on our simulation, it's impossible, right? If we're just basing it on those 50. So the p-value is 0 for Joy because she didn't get 12 in any of them. Or you could think of it as, well, she got it one time, so it would be, the p-value would be 1 out of 50 would be the, or 1 out of 51, because her last one would be the 51st trial. You could look at it that way as well, but basically the p-value is approximately 0. So that's the premise of a hypothesis test. We assume the null hypothesis is true and find how much evidence there is in favor of the alternative. Okay, so general guidelines are here. The smaller the p-value, the more evidence we have in favor of the alternative hypothesis. Okay. Now, in public health, in all of science, there was such a large focus on p-values that for a multiple number of reasons, they started to be misused. A lot of people weren't understanding what they meant. They're somewhat hard to understand. And if I have a p-value of 0 or 0.01 for Joy, it's not really telling me how good of a job she's doing, right? I want to know, like, how good is she doing? I'm actually better to just give you the confidence interval. The p-value is fine, and it's still published in a lot of statistical results, and it's still a very valid inference procedure to conduct hypothesis tests. But more and more journals are really trying to encourage people to use confidence intervals because they give you a lot more information. People understand them better. There's just less potential for error. So there's a lot of good reasons why it's good statistical practice to include a confidence interval. There's nothing wrong with including both. You can say I got a p-value of 0.01, but you know, here's the confidence interval that I have for Joy as well, for you know, the proportion of time she's going to get the correct diagnosis. So I'm not going to go through the formula or the process of getting confidence intervals, but I want to show you this survey method from that Gallup poll. So just recall that we found, I believe it was 14% of people said they would avoid medical care if they had COVID symptoms. And on this little blurb here in the survey methods, the Gallup poll says that 2 percentage points is the margin of error for a response near 10%. So let's just go ahead and assume that the margin of error is going to be 2%. And that margin of error is based on a few things that I'm going to show you on the next slide here. So a confidence interval is constructed in a very simple way, and it's always in this format. It comes in this format for any statistic, any parameter that you're trying to make a confidence interval for. You get your sample statistic, you add and subtract a margin of error. That is the definition of a confidence interval. What did you observe? Add and subtract the margin of error, and there is your interval. Now, what is the margin of error? The margin of error is the estimated standard deviation of your sampling distribution, which we use that theoretical, beautiful central limit theorem to get for us. And then we have this critical value, and the critical value is what is determined by how much confidence you want to have. So if I'm using the normal distribution, which let's just assume we are, the critical value is 1.645 for a 90% confidence interval. So I have a confidence interval like this if I only need to be 90% confident. But then if I want to be 95% confident, it goes to 1.96. If I want to be 99% confident, it goes to 2.576. And if I want to be 100% confident, I just say, you know what, my proportion is between 0 and 1. So you just keep getting wider as you need more confidence. So this is that general form. So from the Gallup poll, we had a sample statistic of 0.14. We add and subtract that margin of error that they gave us of 0.02, and we're left with this confidence interval, 0.12 to 0.16. So that means we are 95% confident that the true proportion of people who would avoid medical care with COVID symptoms is between 12% and 16%. And of course, we have to give it that caveat, assuming that, right, that this is a representative sample, right, all of those things, assuming it's not biased. Because if it's a biased sample, then, you know, all bets are off. We can't be 95% confident anymore. Okay, so I am not going to be able to share with you some of the last results, but I do, Emily, do I have time for one more slide, or do you want to finish off with the, okay, great. So I really love this slide because I think it really helps understand, like, you know, when you start saying you're 95% confident, like, what does that actually mean? And this simulation, I think, just really kind of hits it home what it actually means. And this is all based on simulation. If you can look, for example, let me explain to you what it means. So this is a set of 100 different confidence intervals simulated with a sample size of 1,017, just like from the Gallup poll. And we're assuming that the true population proportion is 0.15. So that's what this line represents right here, okay? So that's the beauty of simulation, is we can just say, well, randomly sample 1,017 people from a population with a P of 0.15 and figure out what the sample proportion is and give me a confidence interval. So for the first sample of 1,017 people, I get a confidence interval that's from 0.1, say 25, up to 0.165. So for that one, did I capture the true proportion? Yeah, the true proportion is between 0.125 and 0.165. So I was successful with that confidence interval. So I'm in this like magical world where I know what the true population quantity is, because this is it right here. So in that first simulation, my confidence interval was, you know, it said 0.125 to 0.165, I got 0.15. So I won, you know, that was a good interval. And the next one, I did well there as well. The next one, I captured it. I captured the true population proportion in every single one of these intervals until right here. So right here, I got a sample proportion that was a little bit off, closer to 0.18. Okay, so then when I add and subtract that 2%, I didn't capture the 0.15. Okay, and so that's what, in 100 intervals, I captured the true proportion 98% of the time. And that's what confidence means. It means if I could repeatedly take samples of size 1,017, 95% of the time I would capture the true proportion. In this case, I did even better. I mean, just by random chance, right? It's just a simulation. So I could do it again and I would maybe get 94%. But that's what 95% confidence means. So I just wanted to show you that and make sure, because I feel like that's a really important concept, and really, like, it's just in almost every paper that you see in public health. So so I think that I might start wrapping up so that you guys can get some lunch and let Emily talk about the survey. I just want to say thank you so much. I talked a little, I just didn't cover just a couple things, but it was sure nice getting to share some statistics with you. And again, feel free to contact me with, I think you'll have my contact info, but or you can just Google me on the public health website through UM.
Yeah. Thanks so much, Cindy.
Thank you.
Thank you, everybody. Thank you, Cindy. That was wonderful. I certainly learned a lot. And yes, I'll make sure that they have your contact information. And we do have an evaluation that we want you to fill out. I'm going to put a link to it in the chat box, but I will also email this out later if you don't have time to do it now. But very, very useful. We certainly use that evaluation information. So please fill that out. I will be sending certificates of completion and a link to this video, hopefully in the next week or two. So you'll certainly have these resources as well. We're trying to get as fast as possible on that. And thank you so much. Anything else, Cindy?
I don't think so. No, I just encourage you to just, you know, be confident and try new methods and research out there. It's a lot of fun.
Awesome. Thank you so much. Our next webinar will be May 28th. So feel free to check out our website and be checking your email because we'll be advertising for that one.